Did you know synthetic oil manufactured in Germany operates completely differently than the exact same brand made in Saudi Arabia? Most car owners do not even know how big that difference is. The viscosity breakdown rates for those oils can vary by as much as 30% between production facilities, even when the bottle carries identical labeling. This is not some minor technical detail. This is the difference between an engine lasting 200,000 miles or needing a rebuild at 120,000 miles. The global synthetic oil industry is fragmented across manufacturing standards that barely communicate with each other. While American Petroleum Institute standards dominate marketing conversations, the real differences happen at the refinery level, where base oil production methods create fundamentally different products. A fully synthetic oil produced in Rotterdam using gas-to-liquids technology will perform differently than a synthetic blend manufactured in Houston using hydrocracked petroleum bases, even if both meet American Petroleum Institute Service SN+ certification. Japanese synthetic oil manufacturers follow Japanese industrial standards that prioritize extreme temperature stability over extended drain intervals. The testing protocols measure viscosity retention at -40 degrees Celsius and 150 degrees Celsius simultaneously, creating formulations that excel in temperature cycling but may sacrifice some fuel economy benefits. This approach stems from Japanese automotive engineering philosophy, where thermal management takes precedence over every other consideration. Engines designed in Japan expect oil that maintains film strength during rapid temperature transitions, not necessarily oil that flows easily at startup. The chemical composition reveals the philosophy. Japanese synthetics typically use higher percentages of polyalpha-olefin base stocks blended with ester compounds that bond to metal surfaces at the molecular level. This creates a protective layer that persists even when the engine sits cold for extended periods. German synthetic oils, by contrast, emphasize polyol ester bases that reduce internal friction to microscopic levels, supporting high-revving engines that operate in sustained, high-load conditions. The trade-off shows up in cold weather performance, where Japanese formulations maintain better protection during the critical first 30 seconds after a cold start, while German oils reach optimal operating viscosity faster once circulation begins. Saudi Arabian synthetic production represents a third approach entirely. With access to some of the world's purest crude oil feedstocks and massive gas-to-liquids facilities, Saudi manufacturers can produce synthetic base oils that start from methane rather than petroleum. The process converts natural gas into long-chain hydrocarbons with almost zero impurities, creating a base stock so clean that it requires minimal additive packages. This allows Saudi synthetic oils to maintain their properties for extended periods because there is less contamination to break down the additives. Independent laboratory testing shows Saudi-produced synthetics maintaining their total base number, which measures acid neutralizing capability, for up to 15,000 miles, compared to 10,000 miles for conventional synthetics. The molecular structure differences between these base oils are staggering when examined under spectroscopic analysis. Saudi gas-to-liquids base oils show hydrocarbon chains with nearly perfect uniformity, measuring between 28 and 32 carbon atoms with minimal branching. German hydrocracked base oils display more variation, with chain lengths ranging from 24 to 38 carbons and moderate branching that affects flow characteristics. Japanese base oils often include intentional diversity to optimize performance across temperature extremes, with carefully controlled mixtures of different chain lengths that each contribute specific properties to the final formulation. If you appreciate the value provided, consider leaving a like on this video. European Union regulations introduce another layer of complexity that most consumers never see on the label. The European Automobile Manufacturers Association, abbreviated ACEA, divides oils into categories that American systems do not recognize. ACEAA3 B4 oils must demonstrate fuel economy improvements while maintaining high temperature, high shear viscosity, above 3.5 centipoise at 150 degrees Celsius. This is a significantly higher standard than American Petroleum Institute requirements. Oils meeting this specification will protect European engines designed with tighter tolerances and higher compression ratios, But the same oil might be over-engineered for an American truck engine that prioritizes durability over efficiency. The molybdenum compounds used in German friction modifiers deserve special attention because they represent a fundamentally different approach to reducing engine wear. Molybdenum dialkyl dithiocarbamate forms microscopic sheets on metal surfaces under high pressure and temperature, creating a solid lubricant layer that persists even when oil film thickness becomes marginal. This technology works exceptionally well in the high-pressure fuel pumps common in European diesel engines, but it can cause deposits in port fuel-injected gasoline engines where fuel washing removes the protective layer. American friction modifiers more commonly use organic compounds and zinc dialkyl-dithiophosphate combinations that provide good anti-wear protection without the potential deposit issues in gasoline applications. Russian synthetic oil production follows technical standards inherited from Soviet-era military specifications that prioritized extreme cold weather performance above all else. The base oils must remain pourable at -55 degrees Celsius, a requirement that shapes the entire formulation strategy. Russian manufacturers achieve this using highly refined Group 3 base oils with very high viscosity index ratings, often exceeding 160 compared to 120 for conventional synthetics. This extreme cold weather capability comes with compromises in high-temperature oxidation resistance, making Russian synthetics excellent choices for Arctic operations, but potentially problematic in desert climates. The Russian approach to cold weather performance involves using exceptionally pure base oils, with minimal wax content rather than relying heavily on pour-point depressant additives. This creates oils that naturally resist thickening in extreme cold without the potential for additive separation or crystallization that can occur with heavily treated conventional oils. Russian military specifications require oil to flow through a standard automotive oil pump within 15 seconds of starting at -50 degrees Celsius, a standard that few Western synthetics can meet without specialized Arctic formulations. Chinese synthetic oil manufacturing represents the fastest-growing segment of global production, with quality levels that vary enormously depending on the specific refinery and target market. Top-tier Chinese facilities operated by Sinopec and PetroChina produce synthetic base oils using hydrocracking and hydroisomerization processes that meet or exceed international standards. These facilities supply oil to global brands who bottle it under their own labels. However, the Chinese domestic market also includes lower-grade products marketed as synthetic that contain minimal true synthetic content, relying instead on heavily refined mineral oils with synthetic additives. The Chinese national standard GB allows oils with as little as 20% synthetic base stock to carry synthetic labeling, creating confusion for consumers trying to compare products. The quality divide in Chinese synthetic production reflects the country's rapid industrial development and diverse market needs. Coastal refineries serving export markets employ technology licensed from European and American companies, producing base oils indistinguishable from Western products. Interior refineries serving domestic economy markets often use older hydroprocessing units that produce acceptable but not exceptional base oils. The additive packages also vary dramatically, with export-grade oils using imported additive packages from Lubrizol or Infineum, while domestic oils may use Chinese-produced additives that meet basic requirements without advanced performance features. The testing protocols reveal how different regions prioritize different performance characteristics. The word to remember here is priorities. American testing emphasizes oxidation resistance and deposit control over thousands of miles of highway driving. The sequence tests mandated by the American Petroleum Institute certification run engines for hundreds of hours at sustained high speeds and loads, measuring varnish formation and ring sticking. European testing focuses more on fuel economy and emissions, running shorter cycles that simulate stop-and-go urban driving with frequent cold starts. Japanese testing splits the difference and adds unique cold cranking simulations that measure how quickly oil flows through tight bearing clearances at low temperatures. The American Petroleum Institute Sequence 4. Oxidation test runs a 4-cylinder engine at 150 degrees Celsius oil temperature for 96 hours, measuring viscosity increase and acid formation. European ACE. A testing includes the M111 gasoline engine test that measures sludge and varnish formation during short trip driving with frequent stops and starts. Japanese JASO testing includes unique low-temperature viscosity measurements at -35 degrees Celsius that exceed requirements in milder climates. These different testing philosophies mean that an oil optimized for American sequence testing may struggle in European urban driving conditions, while a European-tested oil might not provide adequate protection during sustained American highway speeds. Match oil origin and specifications to your engine and local conditions to get the best performance. The viscosity grade systems themselves differ in subtle but important ways. When a European oil displays a 5W30 viscosity rating, the testing methodology differs from American 5W30 standards. European high-temperature, high-shear viscosity requirements are stricter, so a 5W30 that meets European tests will be slightly thicker at operating temperature than its American counterpart. This matters for modern engines with variable valve timing and direct injection systems that depend on precise oil viscosity to operate correctly. Using an oil formulated for European standards in an American engine might result in sluggish valve timing response, while using American spec oil in a European engine might allow excessive wear in high-load situations. Australian synthetic oil specifications reflect the country's unique combination of extreme heat, long-distance driving, and heavy-duty applications. Engines often run where desert heat and sustained highway speeds combine, sometimes for thousands of miles between service points. Australian oil makers respond with formulations that emphasize oxidation resistance and viscosity retention over extended drain intervals. The testing standards include high-temperature cycling that simulates outback conditions, where engine temperatures can spike dramatically when vehicles go from highway speeds to slow, crawling operation over rough terrain. Australian synthetic formulations also account for severe dust in rural and outback areas. The red dust across much of inland Australia consists of extremely fine particles that can bypass air filtration and contaminate engine oil through the crankcase ventilation system. Australian detergency packages use higher concentrations of metallic detergents that chemically bind to dust particles, preventing them from agglomerating into abrasive sludge. This approach differs from Middle Eastern formulations that rely more on ashless dispersants, reflecting different dust composition and engine designs common in each region. The refining processes themselves create fundamental differences that persist regardless of additive packages. American hydrocracked Group 3 base oils begin as conventional crude oil that undergoes severe hydroprocessing to break down and rebuild molecular structures. This process removes impurities and creates more uniform molecular chains, but the resulting base oil still contains some aromatic compounds and variation in molecular weight. European gas-to-liquids Group 3+ and Group 4 base oils start from natural gas or coal, building up hydrocarbons from simple molecules into precisely controlled synthetic structures. This bottom-up approach creates purer base oils with more consistent properties, but it requires significantly more energy and investment. The hydrocracking process used for American Group 3 production operates at pressures exceeding 2,000 pounds per square inch and at temperatures above 400 degrees Celsius. Hydrogen molecules break apart long hydrocarbon chains and saturate double bonds, creating more stable molecules with improved oxidation resistance. However, this process cannot achieve the molecular uniformity of gas-to-liquid synthesis because it starts with complex crude oil containing thousands of different hydrocarbon species. The best hydrocracking can produce is a narrower distribution of molecules, not the nearly perfect uniformity achievable with synthetic construction from simple building blocks. The certification maze grows more complex when considering military specifications that different countries maintain for their defense applications. United States MELPRF specifications for aircraft and ground vehicle lubricants set extremely demanding standards that civilian oils rarely meet. NATO countries follow Allied quality assurance publications that harmonize some specifications across member nations, but still allow national variations. Russian GOST standards for military oils differ significantly from Western approaches, emphasizing extreme cold performance and long storage stability. These military specifications drive innovation that eventually filters into civilian products. but the timeline and path differ by country. Military lubricant specifications often require performance characteristics irrelevant to civilian applications, but representing cutting-edge technology. United States MLPRF specifications include requirements for operation in nuclear, biological, and chemical contaminated environments, resistance to fuel and hydraulic fluid contamination, and storage stability for 20 years or more. These demanding requirements push manufacturers to develop advanced base stocks and additive technologies that eventually find their way into high-performance civilian oils. Military testing also includes environmental exposure protocols far more severe than civilian standards, including salt spray testing, extreme humidity cycling, and thermal shock resistance. Mexican synthetic oil manufacturing has modernized significantly as the country's automotive industry has expanded. Mexican refineries produce Group 3 base oils that supply both domestic demand and export markets. The oils formulated for Mexican conditions must handle high-altitude operation in cities like Mexico City, where thin air affects combustion and cooling, as well as coastal humidity that can promote rust and corrosion. Mexican specifications often reference American Petroleum Institute standards, but include additional requirements for high-altitude performance and resistance to fuel dilution from Mexican gasoline formulations. High-altitude engine operation presents unique challenges that Mexican oil formulations must address. At Mexico City's elevation of 2,240 meters above sea level, atmospheric pressure is approximately 78% of sea level pressure. This reduced pressure affects combustion efficiency and increases blow-by, allowing more unburned fuel and combustion gases to contaminate engine oil. Mexican synthetic formulations include more robust detergent and dispersant packages to handle increased contamination rates, plus rust inhibitors to combat moisture accumulation from incomplete combustion in thin air. The price differences between synthetic oils from different countries often reflect more than just manufacturing costs. European synthetic oils typically command premium prices because of stringent environmental regulations that increase production expenses. European refineries must meet strict emission standards and waste disposal requirements, and those regulations add overhead to every liter produced. Asian synthetic oils can be more competitively priced because of lower labor costs and less restrictive environmental rules, although quality can match or exceed European standards depending on the manufacturer. Middle Eastern synthetic oils benefit from proximity to feedstock sources and government subsidies for petroleum industries, sometimes resulting in world-class products at surprisingly reasonable prices. The environmental compliance costs for European refineries include carbon emission credits, wastewater treatment, and hazardous waste disposal, and these can add 10 to 15% to production costs. European regulations also require extensive environmental impact documentation and periodic regulatory audits, which consume administrative resources. Asian refineries operating in countries with less stringent environmental oversight avoid many of these costs, allowing more competitive pricing even when using similar technology and producing comparable quality products. This cost differential drives some Western oil brands to source base oils from Asian refineries for products sold in price-sensitive markets. The additive chemistry varies not just between countries, but between regions within countries, based on local fuel quality and driving conditions. Synthetic oils formulated for California must include additive packages compatible with the state's strict emissions requirements and reformulated gasoline. The same brand's synthetic oil sold in Texas might use different detergency additives suited to conventional gasoline and less restrictive emissions equipment. European countries with high diesel adoption rates demand different additive balances than Asian countries, where gasoline engines dominate. This regional variation means that oil carrying identical brand names and viscosity ratings can have measurably different formulations depending on where it is sold. California's reformulated gasoline contains oxygenates and has different volatility characteristics than conventional gasoline, affecting how combustion byproducts contaminate engine oil. California-specific oil formulations adjust detergent and dispersant packages to handle these different contaminants while maintaining compatibility with California's unique emissions equipment requirements. The state's focus on reducing particulate matter emissions also drives oil manufacturers toward lower volatility-based stocks that resist evaporation and reduce oil consumption, which contributes to particulate emissions through tailpipe oil burning. The storage stability of synthetic oils reveals another dimension of international differences. Oils manufactured in hot climates must resist degradation during storage and transportation in extreme heat. Middle Eastern and Southeast Asian synthetics include more robust antioxidant packages to prevent breakdown while sitting in storage tanks or warehouse shelves at temperatures that can exceed 40 degrees Celsius. European and North American synthetics face different storage challenges, primarily maintaining pourability after extended cold storage. These environmental stresses push formulators toward different additive strategies even when the finished product will perform the same in an engine. Storage oxidation represents a significant challenge for synthetic oils in hot climates. Even sealed containers allow minimal oxygen permeation, and elevated temperatures accelerate oxidation reactions between oxygen and oil molecules. Middle Eastern formulations combat this with hindered phenol antioxidants that scavenge free radicals formed during oxidation, plus secondary amine antioxidants that decompose peroxides before they can propagate oxidation chains. The combination provides protection during storage periods that may exceed 2 years in distribution channels from refinery to consumer, maintaining oil quality despite harsh thermal exposure. The biodegradability requirements imposed by some European countries have pushed manufacturers toward ester-based synthetics that break down more readily in the environment if spilled. These bio-based, readily biodegradable synthetics often use rapeseed oil derivatives or other plant-based esters combined with synthetic base stocks. The performance can equal or exceed conventional synthetics while offering better environmental profiles. However, these environmentally friendly formulations cost more to produce and may have shorter shelf lives due to the natural ester content. American manufacturers face less pressure to develop biodegradable options, allowing them to optimize purely for performance and cost. European biodegradability standards require oils to achieve 60% biodegradation within 28 days, according to OECD testing protocols. Meeting this standard while maintaining performance requires a careful balance between biodegradable ester content and durable synthetic base stocks. Some European manufacturers use combinations of synthetic esters derived from renewable sources, blended with mineral or synthetic bases to achieve acceptable biodegradability without sacrificing oxidation resistance or thermal stability. These hybrid formulations represent compromises between environmental responsibility and technical performance, with properties falling between fully biodegradable natural oils and conventional petroleum-based synthetics. The contamination tolerance of synthetic oils differs based on the fuel quality they are designed to encounter. European synthetic oils expect ultra-low sulfur diesel with sulfur content below 10 parts per million, and premium gasoline with strict quality controls. These oils may struggle when exposed to lower-grade fuels found in developing markets. Asian and Middle Eastern synthetics often include more robust detergency packages and higher total base numbers to neutralize contaminants from variable fuel quality. This makes them more forgiving in real-world conditions where fuel quality cannot be guaranteed, but it adds cost to the formulation. Fuel sulfur contamination creates sulfuric acid during combustion, which mixes with engine oil and requires neutralization by alkaline detergent additives. European oils formulated for 10 parts per million sulfur fuel contain minimal alkaline reserve because little acid formation occurs. These same oils quickly become acidic when used with higher sulfur fuels common in developing markets, leading to corrosive wear of bearing surfaces and cylinder walls. Asian formulations designed for mixed fuel quality include a total base number of 10 to 12 milligrams of potassium hydroxide per gram, compared to 6 to 8 milligrams per gram for European oils, providing buffer capacity for varying fuel quality. The racing and performance oil sector shows even more dramatic international differences. Italian racing oil manufacturers like Agip and Motul develop formulations specifically for high-revving, naturally aspirated engines common in European motorsports. These oils use very low viscosity bases with extreme shear-stable polymer packages that maintain film strength at 8,000 revolutions per minute and above. American racing oils tend toward heavier base weights, designed for large displacement V8 engines running sustained loads at lower engine speeds. The additive packages reflect these different priorities, with European racing oils emphasizing thermal stability, and American racing oils focusing on anti-wear protection under massive cylinder pressures. Italian racing oil development benefits from direct involvement with Formula One teams and motorcycle Grand Prix racing, where oil performance directly impacts competitive success. These racing applications demand oils that can withstand oil temperatures exceeding 170 degrees Celsius, while maintaining film strength under loads that would collapse conventional lubricant films. Italian manufacturers develop ester-based racing oils using complex pentaerythritol and trimethylolpropane esters that remain fluid at extreme temperatures, while providing boundary lubrication through chemical bonding to metal surfaces. These technologies eventually migrate to high-performance street oils, though in diluted form suitable for longer drain intervals and emission system compatibility. British synthetic oil production maintains traditions dating back to the early development of synthetic lubricants during World War II. Companies like Castrol pioneered synthetic ester technology for aircraft engines, and that heritage continues in modern formulations. British synthetics often contain higher percentages of complex ester compounds than synthetics from other countries, providing exceptional protection in air-cooled and high-performance applications. The trade-off is higher cost and somewhat shorter drain intervals due to ester degradation over time. British formulations also tend to include more anti-foam additives to handle the severe oil churning that occurs in high-performance engines with aggressive crankcase ventilation. British ester technology development during wartime focused on creating lubricants that could withstand the extreme temperatures and loads in aircraft piston engines operating at high altitudes. These early synthetic esters used neopentyl polyol bases combined with synthetic carboxylic acids, creating molecules with exceptional thermal and oxidative stability compared to mineral oils. Modern British racing and performance oils continue this tradition, using advanced ester formulations that provide superior protection in demanding applications, despite higher costs and more frequent change intervals compared to conventional synthetics. Canadian synthetic oil specifications must address the country's extreme temperature range, from -40 degrees Celsius winter cold in the prairie provinces to +35 degrees Celsius summer heat. Canadian synthetics use very broad viscosity index improvers that maintain fluidity in extreme cold while preventing excessive thinning in summer heat. The testing protocols include severe cold temperature pumpability tests that measure how quickly oil reaches critical engine components during winter starts. These requirements push Canadian manufacturers towards synthetic bases with naturally high viscosity indexes, rather than relying heavily on polymer additives that can shear down over time. Canadian cold start testing includes unique protocols that simulate prairie winter conditions, where vehicles may sit unused for weeks at -40 degrees Celsius before requiring immediate cold starts. These tests measure not just oil pourability, but also the time required for oil pressure to build at the main bearings and cylinder head, ensuring adequate lubrication within seconds of starting despite extreme cold. Canadian formulations achieve this through careful selection of polyalpha-olefin base stocks with viscosity indexes exceeding 150, combined with minimal polymer content to avoid viscosity loss from mechanical shearing during cold start conditions. Turkish synthetic oil manufacturers occupy an interesting middle ground between European and Middle Eastern approaches. Turkey's geographic position and diverse climate conditions drive formulations that must perform in Mediterranean coastal heat, mountainous winter cold, and everything in between. Turkish synthetics often blend European ester technology with Middle Eastern thermal stability additives, creating versatile oils suitable for varied operating conditions. The local automotive market includes both European diesel vehicles and older carbureted gasoline engines, requiring oil formulations that can serve multiple applications without specialized variants for each engine type. Turkish market diversity drives oil manufacturers toward jack-of-all-trades formulations that sacrifice peak performance in any single condition for acceptable performance across broad operating ranges. Turkish synthetics typically use Group 3 base oils with moderate ester content, balancing cost with performance. The additive packages combine European-style low SAPS detergents for modern diesel engines with traditional zinc anti-wear additives for older gasoline engines, creating formulations that work adequately in vehicles spanning 4 decades of automotive technology. This approach differs from more specialized European oils optimized for specific engine generations. The polymer technology used in viscosity index improvers varies significantly between manufacturing regions. American polymer manufacturers, such as Infinum, produce olefin copolymer viscosity modifiers optimized for shear stability in automatic transmissions and high-mileage engines. Japanese polymer technology emphasizes star polymers with tightly controlled molecular weight distributions that resist permanent viscosity loss. European manufacturers have developed dispersant viscosity improvers that serve dual functions, maintaining viscosity and keeping contaminants suspended. These different polymer approaches mean that two oils with identical cold and hot viscosity ratings can behave very differently under high shear conditions or after extended use. American olefin copolymer viscosity modifiers use ethylene and propylene monomers polymerized into long chains that thicken oil through their physical size and shape. These polymers align with oil flow at low shear rates, maintaining viscosity, but they temporarily align during high shear events, allowing viscosity to drop and reduce friction. The main challenge is preventing permanent polymer chain breaking during severe mechanical shearing, which causes permanent viscosity loss. American manufacturers address this through careful control of molecular weight distribution, creating polymer populations with few extremely long chains that are susceptible to shearing while maintaining adequate thickening power. Iranian synthetic oil production operates under unique constraints because international sanctions limit access to advanced additive technology. Manufacturers compensate by using exceptionally high-quality domestic crude as feedstock and by focusing on refining excellence rather than on sophisticated additive blends. The resulting synthetic base oils have naturally good properties, but they may lack the modern friction modifiers and detergency packages common in Western synthetics. This yields oils that provide adequate protection, but they do not optimize fuel economy or emissions performance. Iranian refineries produce Group 2+ and Group 3 base oils from indigenous crude with naturally low sulfur and low aromatic content. These favorable feedstock properties allow production of decent base oils without the most advanced hydroprocessing equipment needed to convert heavier, more contaminated crudes. However, manufacturers struggle to source cutting-edge additive packages from global suppliers because of sanctions, so they rely on domestic additive production or on older imported technology. The result is competent lubricants that meet basic requirements, but that lag behind international standards for fuel efficiency and emissions control. New Zealand's synthetic oil specifications reflect the country's clean air regulations and relatively mild climate. New Zealand synthetics must meet strict low-emission requirements while providing adequate protection in moderate temperature ranges. The formulations tend toward lighter viscosity grades like 0W20 and 5W30 that improve fuel economy without sacrificing protection in the country's temperate conditions. New Zealand testing protocols include specific measurements for particulate emissions from engine oil consumption, driving manufacturers toward low volatility-based stocks that resist evaporation. New Zealand's isolated geography and small market size create unique challenges for oil formulation. The country cannot support dedicated refineries for premium synthetic base oil production, so manufacturers must import base stocks and blend finished oils locally. This drives New Zealand formulations toward using globally available Group 3 base oils combined with imported additive packages, limiting opportunities for specialized regional formulations. New Zealand oil companies respond by carefully selecting base oil and additive suppliers to create formulations optimized for local conditions within the constraints of imported components, focusing on low-temperature fluidity for alpine regions and oxidation resistance for coastal humidity. The viscosity modifier degradation rates differ substantially between synthetic oils formulated in different countries. European viscosity modifiers must pass severe mechanical shear tests that simulate millions of gear mesh events in transmissions and differentials. American viscosity modifiers face different challenges from sustained high-temperature operation in oxidizing conditions. Japanese viscosity modifier technology focuses on maintaining viscosity across extreme temperature cycling. These different priorities result in polymer packages that may excel in one type of service while showing weaknesses in another, even though all meet basic viscosity grade specifications. Mechanical shear testing protocols reveal fundamental differences in polymer design philosophies between regions. European Kurt Orban diesel injector shear tests subject oil to severe mechanical shearing by pumping it through diesel fuel injectors thousands of times, measuring permanent viscosity loss. This test simulates the extreme shearing that occurs in modern high-pressure fuel injection systems, where oil serves as the lubricant. American tests focus more on bearing shear at high temperature, reflecting concerns about viscosity loss in engines with worn bearings or aggressive performance driving. Japanese tests emphasize thermal shear under temperature cycling, measuring polymer stability through repeated heating and cooling cycles. The future of synthetic oil manufacturing shows regional patterns driven by environmental regulations and energy policies. European manufacturers invest heavily in bio-based synthetic esters and renewable-based stocks to meet carbon reduction targets. Asian manufacturers focus on cost-effective Group 3 production, using abundant natural gas feedstocks. American producers balance traditional petroleum-based synthetics with newer technologies as regulations evolve. Middle Eastern countries leverage their energy resources to produce ultra-pure synthetic bases for export markets. These diverging paths mean that synthetic oil technology will likely become more regionally specialized, rather than converging toward universal formulations. European investment in bio-based synthetics reflects aggressive carbon neutrality targets, requiring reductions in greenhouse gas emissions across all industrial sectors. Synthetic oil manufacturers contribute by sourcing base oils from renewable feedstocks like used cooking oil or purpose-grown oleochemical crops. These bio-based Group 3 base oils undergo the same hydroprocessing as petroleum-derived oils, producing chemically identical molecules from different starting materials. The carbon footprint reduction comes from using renewable feedstocks that recycle atmospheric carbon rather than extracting fossil carbon, making these oils attractive despite somewhat higher production costs compared to conventional petroleum-based synthetics. The quality control testing frequency and methodology varies dramatically between manufacturing countries. German refineries test every production batch for 20 or more parameters, including viscosity, flash point, pour point, oxidation stability, and additive concentration. Japanese facilities conduct similar comprehensive testing, but they add unique measurements for foam tendency and air release properties. Chinese facilities may test less frequently depending on the market tier they serve, with export-grade oils receiving rigorous testing, while domestic economy oils get spot-checked periodically. American refineries focus heavily on oxidation and deposit testing to ensure long drain interval capability. These different quality control philosophies affect batch-to-batch testing and consistency, and long-term consistency and reliability. German quality control protocols include advanced analytical testing beyond basic physical property measurements. Fourier transform infrared spectroscopy analyzes additive package concentration by measuring absorption bands characteristic of specific additive chemistries. Atomic emission spectroscopy determines metallic additive element concentrations with precision to parts per million, ensuring consistent detergent and anti-wear additive levels. German refineries maintain these rigorous standards to support their premium market positioning, justifying higher prices through demonstrated quality consistency. The testing data becomes part of each batch's quality documentation, providing traceability should any performance issues arise in the field. So what does all this mean for someone trying to choose the right synthetic oil? The manufacturing country and testing standards matter more than brand recognition for matching oil to engine requirements. An engine designed in Germany and manufactured in Europe will almost certainly perform better with European specification synthetic oil, regardless of brand. A Japanese engine benefits from Japanese formulation synthetic oils that prioritize temperature stability over fuel economy. American engines designed for lower-grade fuels and longer intervals between services may actually struggle with European oils optimized for ultra-clean fuel and shorter drains. The international synthetic oil landscape continues evolving as new manufacturing technologies emerge and environmental regulations tighten. Understanding these differences helps explain why experienced mechanics often recommend specific oil brands for certain engine types, regardless of marketing claims or price points. The chemistry behind synthetic oil formulation is far more complex and regionally varied than most consumers realize. And those variations have real consequences for engine performance and durability over hundreds of thousands of miles of operation.